We've always been told a comforting story about knowledge. Give it enough time, enough funding, enough clever engineering, and every mystery eventually falls. The atom fell, the gene fell, the far side of the moon fell. So it feels almost natural to assume that if we just build a sharper instrument, a colder detector, a faster computer, we could eventually measure anything about anything. But there is a place in physics where that story quietly breaks down, not because our tools are too weak, but because the universe itself seems to refuse the question. This is the story of that place, the boundary where the very act of looking closely enough begins to erase what you were trying to see. The story of that boundary, actually, begins a full generation before Heisenberg ever sat down with his troublesome calculations in a problem that seemed, at first glance, to have nothing to do with the limits of knowledge at all. In the final years of the 1800s, physicists were struggling with something called the black body radiation problem, the puzzle of predicting exactly how much light and at what colors a perfectly absorbing heated object should glow. The best theory available at the time, built entirely from the well-tested framework of classical physics, predicted something absurd. An object heated to any temperature should radiate an essentially infinite amount of energy at very short wavelengths. A nonsensical result that came to be known, somewhat theatrically, as the ultraviolet catastrophe. Real heated objects obviously don't do this. A glowing coal or a heated iron bar radiates a modest, finite amount of energy, peaking at a particular color and tapering off at both ends, not exploding toward infinity. In 1900, the German physicist Max Planck found a mathematical fix for this problem, though he initially treated it as little more than a convenient trick rather than a description of anything physically real. Planck proposed that energy, contrary to everything classical physics assumed, isn't emitted or absorbed continuously in any amount whatsoever, but only in discrete packets, later called quanta, with a size proportional to the frequency of the radiation and a fixed constant of proportionality that today bears his name. This single assumption, that energy comes in indivisible chunks rather than a smooth continuum, exactly solved the ultraviolet catastrophe and matched the observed glow of heated objects with remarkable precision. Planck himself later described his own discovery as an act of desperation, a mathematical patch he adopted reluctantly because nothing else worked. Without initially believing it revealed anything deep about the true nature of energy. It took Albert Einstein in 1905, the same extraordinary year he published his special theory of relativity, to take Planck's quantum idea seriously as a description of physical reality, using it to explain the photoelectric effect, the way light striking a metal surface knocks electrons loose only above a certain minimum frequency, regardless of how bright the light is, a result that only makes sense if light itself arrives in discrete particle-like packets of energy, later named photons, rather than as a smooth, continuous wave. This work, rather than the theory of relativity for which Einstein is more popularly remembered, is what eventually earned him the Nobel Prize in Physics in 1921. Within barely 2 decades, quantum theory had grown from Planck's reluctant mathematical patch into a full, if deeply strange, description of the atomic world, developed through the collective work of physicists including Niels Bohr, who proposed in 1913 that electrons in an atom could only occupy specific, discrete energy levels rather than any arbitrary orbit, explaining the puzzling, discrete lines seen in atomic spectra. Louis de Broglie, who proposed in 1924 that particles of matter, not just light, could behave as waves, and Erwin Schrödinger, who in 1926 wrote down a wave equation describing how these matter waves evolve over time, an equation that remains, to this day, one of the central pillars of quantum mechanics. It was into this rapidly maturing but still conceptually unsettled field that Heisenberg introduced his uncertainty principle in 1927, and it landed not as an isolated curiosity but as the sharpest, most explicit statement yet of just how differently the quantum world seemed to behave compared to the smooth, deterministic universe that Newton, and later Einstein, had described. To understand how strange this boundary really is, it helps to look closely at a young German physicist named Werner Heisenberg sitting with a stack of calculations that didn't behave the way anyone expected. He was trying to describe, mathematically, where an electron is and how fast it's moving. Two simple questions: position and momentum. In the everyday world, you can answer both at once without any trouble. A baseball has a location and a speed, and knowing one tells you nothing that stops you from knowing the other. Heisenberg found something different buried in the mathematics of the quantum world. The more precisely you pin down where a particle is, the less precisely you can know how fast it's moving, and the reverse is also true. It wasn't a limitation of the microscope. It wasn't a limitation of 1920s technology. It was a limitation built into the structure of reality, expressed today in an equation that says the uncertainty in position, multiplied by the uncertainty in momentum, can never fall below a fixed, tiny number related to Planck's constant. For decades, plenty of physicists, including some very famous ones, hoped this was a temporary embarrassment. Perhaps future physics would find hidden variables, some deeper layer of reality that, if we could just see it, would restore the tidy determinism of a clockwork universe. Albert Einstein spent years unconvinced, famously insisting that the universe doesn't play dice, but experiment after experiment, especially the tests of quantum entanglement carried out from the 1970s through the 2000s. Closed the door on that hope. The randomness isn't a placeholder for ignorance. It's not like not knowing the outcome of a coin flip because you didn't see it land. It's a form of not knowing that exists at the deepest level physics has ever probed. One where the outcome genuinely isn't decided until the moment of measurement. That distinction matters enormously because it separates two very different kinds of not knowing. One kind is practical. If your thermometer isn't precise enough, you can buy a better thermometer. If your telescope isn't powerful enough, you can build a bigger mirror, put it in space, cool its sensors closer to absolute zero. This is the kind of ignorance humanity has been erasing for 4 centuries, and it's the reason we've gone from squinting at Jupiter's moons, through a spyglass, to photographing the shadow of a black hole. The other kind of not knowing is structural. It isn't a statement about the quality of our tools. It's a statement about what the universe permits to exist as a fact in the first place. And it's this second kind, the structural kind, that turns Heisenberg's principle from an interesting complication into something closer to a wall. If you want to appreciate how literal that word wall can be, it helps to zoom in, really zoom in, past the scale of atoms, past the scale of the protons and neutrons inside those atoms, down towards something physicists call the Planck length. It's an almost unimaginably small unit, about 1.6 times 10 to the negative 35 meters, named after the same Max Planck, whose constant appears in Heisenberg's inequality. To put that number in perspective, if you shrank the entire observable universe down to the size of a single atom, the Planck length would still be smaller relative to that atom than an atom is relative to the observable universe today. Nobody has ever probed distances anywhere close to this scale directly. But in the mathematics of general relativity and quantum theory, something curious starts to happen as you approach it. According to Einstein's general relativity, mass and energy curve the geometry of space and time around them. This is why light bends near the sun, why clocks run slightly slower deep in a gravity well, why massive objects can warp space enough to trap light entirely inside black holes. Quantum theory, meanwhile, insists that at very small scales, nothing has a perfectly definite value. Energy itself fluctuates randomly, even in what we'd call empty space, popping virtual particles briefly into and out of existence. Bring these two ideas together at the Planck scale, and you get something physicists sometimes describe with an evocative phrase, quantum foam. Down at that scale, the fluctuating energy is thought to become large enough that it would locally warp spacetime as violently as if you were standing at the edge of a black hole. Except everywhere, all the time, at random, space stops looking like a smooth stage on which particles perform, and starts looking more like a chaotic, foaming sea whose geometry itself is uncertain from one instant to the next. This is still, it's worth being honest, a theoretical extrapolation rather than something anyone has observed. No experiment has directly imaged quantum foam, and it remains possible that a deeper theory, whatever eventually unifies gravity with quantum mechanics, will describe this regime differently than today's rough sketches suggest. But the reasoning that leads there is solid enough and consistent enough across independent approaches to quantum gravity that most physicists take the conclusion seriously. Below the Planck scale, the everyday concepts of distance and duration may simply stop applying in any way we currently understand them. It isn't that a ruler becomes too clumsy to measure something that small. It's that the question how far apart are these 2 points might not have a well-defined answer once the points are close enough, that the geometry between them is dissolving into probabilistic foam. Out of this picture comes something you could call an information horizon, a concept that runs parallel to the more famous event horizon of a black hole but applies to measurement itself. Imagine trying to locate a particle with ever finer precision, to resolve smaller and smaller distances. Quantum mechanics tells you that you need light, or some other probe, with an ever shorter wavelength, which means ever higher energy, because wavelength and energy are locked together by the same Planck relationship that shows up throughout quantum theory. Push that logic far enough, down toward the Planck length, and the energy required to resolve that tinier distance becomes so enormous that, according to general relativity, it would concentrate enough mass energy in that tiny region to form a miniature black hole. At that point, instead of getting a sharper picture, your probe collapses the very region you were trying to examine into a horizon of its own, one that swallows the information rather than revealing it. The measurement, in a very real sense, destroys the thing it was measuring before the result can even be read. This isn't science fiction, dressed up in physics vocabulary. It's a genuine consequence of combining two of the best tested frameworks humanity has ever built, quantum mechanics and general relativity, and noticing that they contradict each other in a specific, calculable way at extremely small scales. That contradiction is one of the central reasons physicists have spent nearly a century searching for a theory of quantum gravity, some deeper framework, whether string theory, loop quantum gravity, or something not yet imagined, that would resolve the tension. Until such a theory exists and is tested, the information horizon remains a prediction rather than a confirmed feature of nature. But it's a prediction built on solid mathematical footing, and it points toward the same unsettling conclusion the uncertainty principle already hinted at. Some information about reality may not merely be hidden from us. It may not exist as a determinate fact at all until the universe, through some process we still don't fully understand, forces a value to appear. If you want an early opportunity to pause and actually think about what this means for how you live, this is a natural place for it. Most of us go through our days assuming that anything unknown is simply unmeasured, a puzzle waiting for the right tool. It's worth sitting, even briefly, with the far stranger possibility that some puzzles were never solvable in the first place. Not because we ran out of cleverness, but because the universe itself never wrote down an answer to look for. If that idea unsettles you a little, or fascinates you, that's exactly the right reaction, and it's worth carrying that feeling forward. Maybe even jotting down the thought so you can return to it, because it will resurface again and again as this story unfolds. To understand why physicists take this boundary so seriously today, rather than dismissing it as an old, half-forgotten worry from the 1920s, it helps to look at how experimental physics has spent the last several decades, pushing directly against the noise floor of the universe. Every measurement, no matter how careful, has to contend with some baseline of randomness that has nothing to do with sloppy equipment and everything to do with the physics of the system being measured. Engineers call this a noise floor. In audio recording, it's the faint hiss you hear even with the volume all the way down and no signal playing, caused by the random thermal jostling of electrons in the wiring. In quantum physics, the noise floor isn't caused by imperfect wiring. It's built into the vacuum itself, even at a temperature of absolute zero, the coldest temperature theoretically possible. Quantum systems don't sit perfectly still. This is a direct consequence of the uncertainty principle applied to energy and time, or equivalently to position and momentum for a particle confined in a small space. A particle locked into place, even in principle, would have a perfectly defined position and, if it were also perfectly still, a perfectly defined momentum of zero. Uncertainty forbids both at once. So nature compromises by giving confined particles a minimum residual jiggling called zero-point energy. A pendulum, cooled to as close to absolute zero as physics allows, doesn't stop. It keeps trembling with a tiny, irreducible motion that no amount of additional cooling can remove, because removing it would violate the uncertainty relation itself. The scale of the engineering challenge involved in even approaching this noise floor is worth appreciating on its own terms, because it represents one of the most demanding precision measurement efforts ever undertaken by human beings. LIGO's detectors work by splitting a laser beam and sending it down to perpendicular tunnels, each several kilometers long, where the light bounces back and forth between mirrors before recombining. A passing gravitational wave stretches one tunnel almost imperceptibly while compressing the other, shifting the pattern of light when the two beams recombine. The stretching involved is so small that it's genuinely difficult to convey with an ordinary analogy, but physicists often describe it this way: if you could stretch the entire distance between the Earth and the nearest star beyond our own sun, the change caused by a typical gravitational wave passing through would amount to roughly the width of a single human hair. To detect a distortion that absurdly small, LIGO's engineers had to eliminate every conceivable source of ordinary noise, isolating the mirrors from seismic vibrations using elaborate multi-stage pendulum suspension systems, holding the entire optical path inside one of the largest and most perfect vacuum systems ever constructed, and cooling and polishing the mirrors to a precision measured in fractions of the width of an atom. And after all of that engineering triumph, painstakingly built up over more than 4 decades of design, funding battles, an incremental improvement since the project's earliest conceptual proposals in the 1970s, the detector's ultimate sensitivity still runs directly into the same quantum noise floor discussed throughout this documentary. The fundamental jitter that no amount of additional engineering, polish, can ever fully remove. This zero-point energy isn't a small footnote confined to textbooks. It shows up directly in extraordinarily sensitive experiments designed to detect the faintest signals in nature, including the detectors built to catch gravitational waves, the Laser Interferometer Gravitational Wave Observatory, known as LIGO, first announced its detection of gravitational waves from colliding black holes in 2015, a discovery that confirmed a century-old prediction of Einstein's and opened an entirely new way of observing the universe. But LIGO's engineers have spent years fighting a persistent adversary baked directly into quantum theory, something called quantum shot noise and its close cousin, radiation pressure noise, both consequences of the same zero-point fluctuations that make the vacuum itself restless. Photons arrive at a detector in discrete, randomly timed bursts, not as a perfectly smooth stream, and the mirrors used to bounce laser light back and forth are nudged, ever so slightly, by the quantum fluctuations of the light itself. Engineers have developed remarkably clever techniques, including something called quantum squeezing, which redistributes uncertainty between two properties of the light, so that one becomes quieter at the cost of making the other noisier, buying precision in the measurement that actually matters for detecting gravitational waves. It's an elegant trick, and it has genuinely improved LIGO's sensitivity. But squeezing doesn't eliminate the uncertainty. It only reshapes it, moving the noise somewhere less inconvenient. Because the total uncertainty allowed by the underlying physics is fixed, this pattern, pushing noise around rather than eliminating it, shows up again and again in the most sensitive instruments ever built. Atomic clocks, which now keep time precisely enough that they would neither gain nor lose a second over many billions of years, are ultimately limited by exactly this kind of quantum noise in the atoms used to define the ticking. Quantum computers, which promise to solve certain problems far faster than any ordinary computer, are built from delicate quantum states called qubits that are extraordinarily vulnerable to a phenomenon called decoherence, in which uncontrolled interactions with the surrounding environment randomize the qubit's information almost as quickly as it's created. Some of that decoherence comes from imperfect engineering, stray electromagnetic fields, tiny vibrations, imperfect materials, and those sources genuinely can be reduced with better isolation and better materials. But some portion of it traces back to the same fundamental uncertainty that makes an isolated particle jitter even at absolute zero. Engineers can chase the fixable noise down for years, and they have, dropping error rates by orders of magnitude across the past 2 decades. What they cannot do, no matter how good the engineering becomes, is chase away the portion of the noise that quantum mechanics itself guarantees will always be there. This is the honest, careful way to describe where experimental physics stands. Researchers around the world, at institutions from the National Institute of Standards and Technology, in the United States, 2 groups working with optomechanical resonators, superconducting circuits, and trapped ions in Europe and Asia, have spent the past 2 decades getting closer and closer to what's called the standard quantum limit, the theoretical floor of measurement precision set by the balance between position uncertainty and momentum uncertainty. Techniques like squeezed light and so-called back-action evading measurements have allowed some experiments to beat the standard quantum limit for specific quantities under specific conditions. A genuinely remarkable achievement that shows the limit isn't always an absolute flaw for every measurement strategy, but no technique has ever violated the deeper uncertainty relation itself, the one Heisenberg wrote down in 1927. Every clever trick simply moves the uncertainty somewhere it matters less for the specific question being asked. It's less like breaking through a wall and more like discovering you can slide along it, finding a slightly more comfortable spot to stand without ever actually getting past it. It's worth pausing on why this matters beyond the walls of a physics laboratory. Every time you use GPS to navigate somewhere, you're relying on atomic clocks aboard satellites that must account for both the effects of Einstein's relativity and the residual quantum noise limiting their precision. every advance in quantum computing that might eventually help design new medicines or new materials depends on engineers understanding exactly which noise sources are fixable and which are fundamental. The wall we're describing isn't an abstract philosophical curiosity confined to blackboards. It's a real, calculable, load-bearing feature of the same physics that quietly runs underneath modern technology. And understanding its shape is part of what allows scientists to know where to keep pushing and where pushing simply won't work. From here, the story moves from noise into something even stranger. The way that observation itself can reach backward and rewrite what already happened, at least according to some of the most carefully verified and most philosophically disorienting experiments in the history of physics. The starting point for this part of the story is the famous double-slit experiment, first performed with light by Thomas Young in 1801, and later repeated with electrons, and then with entire molecules. Throughout the 20th century, the setup is deceptively simple. Fire particles, one at a time, at a barrier with two narrow slits cut into it, and let them land on a screen behind. If particles behaved like tiny bullets, you'd expect two bands to build up on the screen, one behind each slit. Instead, what accumulates over time is an interference pattern, alternating bright and dark bands, the unmistakable signature of waves overlapping and reinforcing or cancelling each other out. Somehow, even when particles ascend through one at a time, with no other particle around to interfere with, the pattern that builds up looks as though each particle passed through both slits simultaneously and interfered with itself. The truly strange part comes when you try to catch the particle in the act, by placing a detector at one of the slits to determine which path it actually took. The moment you do this, the interference pattern vanishes. The particles start behaving like simple, localized objects that went through one slit or the other, landing in two clumps instead of an interference pattern. It's as if the particle knows it's being watched and changes its behavior accordingly. Physicists have spent decades ruling out mundane explanations for this, checking whether the detector itself is somehow physically disturbing the particle enough to destroy the interference through ordinary jostling. In many versions of the experiment, the disturbance really is that simple: a photon detector bumping an electron just enough to blur the pattern. But a special class of experiments, called delayed choice quantum eraser experiments, first proposed conceptually in the 1970s and carried out in various forms from the 1990s onward, was specifically designed to rule out this simple explanation. In a delayed choice quantum eraser setup, researchers use pairs of entangled photons, created together in such a way that measuring one tells you something about the other, no matter how far apart they later travel. One photon from each pair travels toward a double-slit arrangement and is detected on a screen. Its entangled partner travels a separate path toward a set of detectors that can be configured after the first photon has already been recorded on the screen, either to reveal which path information or to erase it. Because of the way the entangled partner's path is chosen after the first photon has already landed, the experimenters can decide whether to know which slit the original photon went through only after that photon's arrival is already a fixed fact in the laboratory's records. And here's the astonishing result, replicated across many independent laboratories. When the researchers choose to erase the witch path information encoded in the partner photon, the correlated subset of the earlier photons, the ones whose partners had their path information erased, shows an interference pattern when you go back and sort the data. When they choose instead to preserve witch path information, that correlated subset shows no interference, just as if a detector had directly measured the path. It's crucial to describe exactly what this does, and does not imply because this experiment gets misrepresented constantly in popular science writing, sometimes in ways that suggest measurements can literally reach backward in time and change the past, as though causality itself runs in both directions. That's not quite what's happening. No signal or information actually travels backward in time in these experiments, and no individual outcome is ever changed after the fact. What's really going on is more subtle, and in some ways even stranger. The outcome recorded on the screen was never a simple, fixed fact of particle went through slit 1 or particle went through slit 2, independent of the entire experimental context, including choices made later about the entangled partner. Quantum mechanics describes an entangled pair as a single, unified system whose properties aren't fully determined until you specify how the whole system, including all its correlated parts, is eventually measured. The pattern doesn't retroactively change. Rather, it was never a fixed, classical fact to begin with, and sorting the data according to the later choice simply reveals which correlations were there all along. Correlations that only make sense once you account for the full set of measurements, present and later, together. This is subtle enough that it's worth restating in a different way. Imagine two envelopes sealed at the same moment, containing correlated but individually random numbers, such that you can only see the pattern connecting them once you open both. Opening the second envelope doesn't change what was already written inside the first one, but it does determine which meaningful pattern you're able to extract when you look at both envelopes together. The delayed choice quantum eraser is doing something conceptually similar, except at the quantum level, where the sealed information isn't merely hidden, but genuinely undetermined until the full measurement context is established. It's less the future is changing the past, and more the past never had the kind of definite, path-specific reality we intuitively assume it did, until the full quantum story, including its later chapters, is told. The delayed choice quantum eraser isn't the only experiment in this family that seems, on the surface, to defy ordinary common sense about how properties belong to objects. A related and similarly counterintuitive effect, first proposed theoretically in 2013 by Yakira Heronov and collaborators, and then demonstrated experimentally with neutrons the following year by a team led by Tobias Denk, has come to be called the quantum Cheshire cat effect, named for the grinning cat in Lewis Carroll's Alice's Adventures in Wonderland that famously vanishes while leaving only its smile behind. In these experiments, physicists use a technique called weak measurement, which extracts a small amount of information about a quantum system, without disturbing it enough to collapse its superposition entirely. To track a particle's location separately from tracking one of its properties, such as its magnetic moment, under carefully engineered conditions, the results suggest that the particle appears to travel down one path while its magnetic moment appears to travel down a completely different path, as though the property had become detached from the particle carrying it. In the same way, Carroll's cat's grin lingered after the rest of the cat had disappeared. As with the delayed choice quantum eraser, this doesn't mean a magnetic moment literally floats through space independent of any particle in some spooky, magical sense. It means that at the quantum level, the ordinary, intuitive assumption that a particle and its properties are always bundled together as a single, indivisible package moving along a single, definite path turns out to be another one of those hidden assumptions, built entirely from experience with the ordinary-sized world, that quantum mechanics is willing to violate under the right experimental conditions. Physicists studying this entire family of experiments, from the double-slit apparatus to the delayed choice quantum eraser to the quantum Cheshire cat, have increasingly converged on a shared conclusion, even while continuing to disagree about the deeper interpretation All of these experiments reveal that the properties we normally treat as fixed characteristics that objects simply carry with them, location, momentum, magnetic moment, even the distinction between before and after in some of the delayed choice variants are, at the quantum level, better understood as relationships that only become fully definite once a complete measurement context has been specified, rather than as intrinsic labels a particle carries around independent of how or whether anyone chooses to look. This has led some physicists to explore an interpretation called retrocausality, most notably developed and defended by figures including the physicist who Price and later explored quantitatively by researchers including Ken Wharton, which proposes that some of these puzzles become easier to make sense of if you allow influences to travel backward in time under very specific, tightly constrained conditions, rather than insisting that all causation must run strictly from past to future. It's crucial to be precise about what a serious retrocausal proposal actually claims, because it bears no resemblance to popular notions of time travel or changing the past. A rigorous retrocausal model still produces exactly the same standard experimental predictions as ordinary quantum mechanics. It never allows any observer to send a usable signal backward in time, receive information from their own future, or alter an outcome that has already been recorded. What it offers instead is a different, arguably more symmetric way of accounting mathematically for why measurement choices made later in an experiment appear correlated with outcomes recorded earlier, treating the apparent asymmetry between past and future as a feature of how humans experience time rather than as a feature written into the fundamental equations themselves. Retrocausal models remain a minority position within the physics community, one serious option among several competing interpretations rather than an established consensus. And it's entirely possible that future theoretical or experimental work will rule the approach out entirely, or alternatively, that it will turn out to offer real advantages current interpretations lack. What all of these competing interpretations agree on, regardless of which one eventually wins out, is the experimental bedrock underneath them, the measurements themselves, endlessly repeated, endlessly verified across independent laboratories on different continents, keep coming back with results that no theory built on ordinary, everyday intuitions about definite, independent, time-ordered properties can reproduce. Even with that more careful framing, the implications are still enormous for how physicists think about causality and information. It suggests that asking which path did the particle really take might be a question the universe simply never answers, in the same way that asking what color is a shadow doesn't have an answer beyond it depends what's casting it and what's behind it. The question itself may be built on a hidden assumption that particles always have a definite trajectory whether or not anyone checks, an assumption that quantum mechanics has been undermining since the very beginning of the field. Niels Bohr, one of the founders of quantum theory, argued exactly this back in the 1920s and 30s, insisting that it's meaningless to ask about a quantum system's properties independent of a specified measurement setup, a position that placed him in direct, sustained intellectual conflict with Einstein for the remainder of both men's careers. Their disagreement played out publicly across a series of legendary exchanges at the Solvay physics conferences held in Brussels, particularly in 1927 and again in 1930, where Einstein would arrive with an ingenious new thought experiment each morning designed to expose some hidden inconsistency in quantum theory, and Bohr, often working through the night, would return the following day with a rebuttal, usually turning Einstein's own thought experiment against him using the very same relativity and quantum principles Einstein trusted most. Colleagues who witnessed these exchanges described them as some of the most intense and consequential intellectual sparring matches in the history of science. Two of the greatest minds of the century, each convinced the other was missing something essential about the deepest nature of reality. The disagreement reached its most precise and enduring form in 1935, when Einstein, together with the younger physicists Boris Podolsky and Nathan Rosen, published a paper now known by the initials of its three authors, the EPR paper, laying out what has become one of the most famous thought experiments in the history of physics. The argument imagined two particles created together in a way that quantum mechanics predicts should remain correlated no matter how far apart they later travel. Exactly the entangled pairs later used in the delayed choice quantum eraser experiments described earlier in this story. Einstein, Podolsky, and Rosen argued that if you could measure one particle and instantly know something definite about its distant partner, without disturbing that partner in any way, then the distant particle must have possessed that definite property all along, whether or not anyone measured it, since nothing could have traveled between the two particles fast enough to create the correlation at the moment of measurement without violating the speed limit imposed by relativity. If quantum mechanics didn't describe that pre-existing, definite property, they argued, then quantum mechanics itself must be an incomplete description of reality, missing some deeper layer of so-called hidden variables that determined the outcome all along. Einstein privately, and somewhat dismissively, referred to the strange, faster-than-light seeming correlation implied by the alternative reading as spooky action at a distance, a phrase that has stuck in popular science writing ever since, even though, as physicists have since clarified at length, the correlations revealed by entanglement can never actually be used to send a usable signal faster than light, a subtlety that keeps the effect fully compatible with relativity even though it remains deeply strange. For nearly 30 years, the EPR paper sat as a brilliant, unresolved philosophical challenge, admired for its clarity but seemingly untestable, since it wasn't obvious how any experiment could distinguish between the particles secretly had definite properties all along and the properties genuinely didn't exist until measurement created them. That changed in 1964 when the Northern Irish physicist John Stuart Bell found a way to turn the philosophical dispute into a precise mathematical inequality, now called Bell's inequality, that any theory relying on Einstein's preferred hidden, pre-existing definite values would have to satisfy, and that quantum mechanics, if taken at face value, predicted would sometimes be violated. This transformed an apparently unanswerable philosophical question into a concrete experimental one. Build the right apparatus, measure enough entangled particle pairs, and check whether the statistics obey Bell's inequality or break it. Decades of experiments, including tests of Bell's inequalities carried out from the 1960s onward by physicists like John Clauser, Alan Aspect, and Anton Zeilinger, work recognized with the Nobel Prize in Physics in 2022, have shown that no theory relying on hidden, pre-existing definite values, the kind Einstein hoped for, can reproduce the statistics that quantum mechanics actually predicts and experiments actually confirm. Reality, at this level, genuinely does not seem to carry hidden answer sheets waiting to be read. If particles don't carry hidden answer sheets, then the wall we've been describing starts to look less like a barrier standing between us and a definite truth, and more like a description of the fact that certain truths simply aren't definite until measurement happens. And even then, definite has to be understood relative to the entire experimental context, not as some absolute, view from nowhere fact sitting quietly in the particle the whole time. This is where a philosophical frustration starts to creep into even the most rigorous physics departments. The traditional scientific method, going back to Galileo and Francis Bacon, assumes there's an objective reality out there, doing whatever it does, regardless of whether anyone's watching. And that careful observation gradually reveals that hidden order. Quantum mechanics, taken at face value, seems to say that at the smallest scales, the act of specifying a measurement is part of what brings a definite fact into existence in the first place. That's not a limitation of the scientific method exactly, since the method still produces astonishingly precise, testable, repeatable predictions. But it does mean the method's traditional target, an observer-independent fact waiting quietly to be discovered, may not be the right target at every scale of nature. Some physicists have tried to push this frustration even further with a thought experiment first proposed by Eugene Wigner in the 1960s, now generally called the Wigner's friend scenario. Imagine a friend of yours inside a sealed laboratory, performing a quantum measurement on some particle, say, checking whether an unstable atom has decayed or not. From your friend's perspective, standing inside the lab, the measurement has a definite outcome the moment it happens. The atom either decayed or it didn't, full stop. But if you, standing outside, treat the entire sealed laboratory, including your friend, as a single quantum system that you haven't yet measured, the mathematics of quantum theory describes the whole lab, friend included, as existing in a superposition of both outcomes simultaneously, at least until you open the door and look inside. Two valid descriptions, from two different perspectives, seem to disagree about whether a definite fact exists at all before you open that door. In the last decade, physicists, including Časlav Bruckner, have proposed experimentally testable variations of this scenario. And in 2019, a team led by researchers in Australia, including Massimiliano Proietti, carried out a version of the experiment on a small scale using entangled photons standing in for the observers. The results were consistent with the unsettling reading. There may be no single, universally agreed upon fact about when, exactly, a measurement outcome becomes definite, only different, equally valid accounts relative to different observers. It's important to be careful here too, because this remains an active area of interpretation and debate, not a settled conclusion. And different schools of thought within quantum foundations, from everation many worlds approaches to objective collapse models to relational quantum mechanics, handle the Wigner's friend scenario in genuinely different ways. What's not in dispute is the experimental result itself. Entangled photon systems really do behave in ways that resist a single, observer-independent story about what really happened. And any complete theory of quantum mechanics has to somehow account for that. This same puzzle, the question of exactly when and how a fuzzy quantum possibility turns into a single, definite classical fact, is often called the measurement problem. And it has haunted physics since almost the very beginning of the quantum era. The most famous illustration of it was never meant to be taken literally, and it's worth clearing up exactly what its author intended, because it's one of the most widely misunderstood thought experiments in the history of science. In 1935, the Austrian physicist Erwin Schrödinger, one of the founders of quantum mechanics and no fan of some of its stranger implications, proposed a scenario specifically to highlight how absurd he found the idea that quantum superposition could apply to large, everyday objects. Imagine sealing a cat inside a box together with a small amount of a radioactive substance, a detector that will trigger a mechanism to release a poison if the substance decays, and no way for anyone outside to observe what happens inside, because the decay of the radioactive atom is a genuinely random quantum event, following exactly the kind of uncertainty discussed throughout this story. Quantum mechanics describes the atom, prior to observation, as existing in a superposition of having decayed and not having decayed simultaneously. If you take the mathematics of quantum superposition completely, literally, and apply it all the way up to the scale of a cat. The unopened box would then contain a cat that is, in some sense, simultaneously alive and dead, a superposition of two entirely incompatible macroscopic states. Until someone opens the box and looks. Schrödinger intended this as a reductio ad absurdum, a deliberately uncomfortable illustration meant to expose what he saw as a gap in how physicists of his era were interpreting the mathematics, rather than as a serious proposal that cats can literally be alive and dead at once. And indeed, no one has ever observed anything resembling a superposed cat. And there are good physical reasons to think no one ever will. The answer to why quantum superposition, so thoroughly confirmed for individual particles, and even for reasonably large molecules, doesn't obviously show up for cats, chairs, or people involves a phenomenon called dicoherence, extensively developed, theoretically from the 1970s onward by physicists including Heinz, Zay, and later Warczek. Zurich dicoherence describes how an object's quantum superposition rapidly leaks out into its surrounding environment, entangling with the countless air molecules, photons, and other particles constantly bumping into it, so quickly and so thoroughly that any interference effects between the alive and dead branches become utterly undetectable in practice within an almost unimaginably short span of time for anything as large as a cat. The superposition doesn't necessarily vanish in some deeper mathematical sense, at least according to certain interpretations of quantum theory, but it becomes so thoroughly entangled with its environment that no experiment anyone could plausibly perform would ever be able to detect the interference that would prove it was still there. This is part of why the wall discussed throughout this story is so hard to notice in ordinary life. Decoherence acts like an extremely efficient curtain, drawn almost instantaneously across anything larger than a molecule, hiding the underlying quantum uncertainty from view long before it could ever become a practical, everyday puzzle. Physicists have spent decades testing exactly where that curtain falls, and the results are genuinely remarkable. Experiments carried out by groups including Anton Zeilinger's team in Vienna have demonstrated interference patterns, the signature of quantum superposition, using molecules containing hundreds of atoms, including complex carbon-based molecules built specifically for these tests. Every few years, the record for the largest object shown to exhibit quantum interference creeps upward, as experimentalists find cleverer ways to isolate larger and larger systems from the decohering influence of their environment for just long enough to catch a glimpse of their quantum nature before it vanishes. Separately, a different class of experiments has pushed in the opposite direction, taking genuinely macroscopic objects, tiny vibrating drumheads, and mirrors visible without a microscope, and cooling them so completely and isolating them so carefully that they can be placed into quantum superpositions of vibrating and not vibrating, work recognized as some of the most delicate experimental physics ever performed. Neither line of research has found any evidence of a special boundary where quantum mechanics simply stops applying and classical physics takes over by some separate, different set of rules. Instead, what emerges is a picture where not a sudden switch from quantum to classical law explains the entire transition, growing more and more effective as objects get larger, more complex, and more entangled with their surroundings, but never actually replacing the underlying quantum description with anything fundamentally different. The wall, in other words, doesn't sit at some special size of object. It sits at the boundary of what any observer, however clever, can practically extract as usable information. Once decoherence has done its work, there's a further layer to this puzzle worth exploring. because it connects the measurement problem directly back to the information horizon described earlier in this story. Some physicists, including proponents of an interpretation called objective collapse theory, developed independently by Giancarlo Garofalo, Alberto Rimini, and Tullio Weber in the 1980s, and later refined by Roger Penrose with an explicitly gravitational twist, have proposed that superpositions don't just become practically undetectable through decoherence, but genuinely, physically collapse into one definite outcome once a system crosses some threshold of size or mass, through an actual physical mechanism rather than merely an entanglement with the environment. Penrose specifically proposed that gravity itself might be responsible, suggesting that a sufficiently massive object placed into superposition would create two subtly different curvatures of spacetime, one for each branch of the superposition, and that spacetime itself becomes unstable when forced to support two contradictory geometries at once, resolving the instability by collapsing the superposition into a single, definite outcome within a calculable amount of time. This remains a minority position among physicists, and it makes a specific, testable prediction that differs, at least in principle, from the standard decoherence picture, which is part of why several experimental groups around the world have begun designing extraordinarily delicate tests involving tiny masses held in quantum superposition for as long as possible while carefully screening out ordinary specifically to check whether Penrose's proposed gravitationally induced collapse actually occurs at the rate his theory predicts, or whether standard quantum mechanics, without any additional collapse mechanism, continues to hold all the way up. As of the most recent published results, no such gravitationally induced collapse has been detected, and the experiments have already ruled out some of the simplest versions of the proposal. But more sensitive versions of the test remain squarely within reach of the next generation of experimental technology, making this one of the genuinely open, actively contested frontiers of physics discussed throughout this documentary. Step back from the philosophical vertigo for a moment and consider the practical, technological side of this same story, because it turns out that the very same spooky features Einstein distrusted have become the foundation of entirely new industries. Quantum entanglement, the phenomenon underlying both the delayed choice, quantum eraser, and the Wigner's friend experiments, is now the working principle behind quantum cryptography, a technique that uses the fragility of quantum measurement as a security feature rather than an inconvenience, because measuring a quantum system generally disturbs it. Any eavesdropper trying to intercept an entangled quantum communication channel leaves detectable fingerprints, an idea first proposed by Charles Bennett and Gilles Brassard in 1984 and now deployed in real fiber optic networks and even satellite-based systems, including China's Michus satellite, launched in 2016, which has demonstrated secure quantum key distribution across continental distances. The uncertainty that seems, at first, like an obstacle to knowledge turns out to be repurposed in these systems as a genuine safeguard, precisely because disturbing a quantum system to spy on it necessarily leaves a trace. What looks like a wall from one angle becomes a locked door with a very reliable alarm system from another. This dual nature, obstacle and resource simultaneously, is worth sitting with, because it changes the emotional tone of the whole story. It would be easy to frame quantum uncertainty purely as a loss, the universe cruelly withholding secrets from curious minds, but physicists have increasingly learned to treat it instead as a genuine feature of nature with its own internal logic, one that once understood can be worked with rather than merely lamented. That reframing from the wall that stops us to the shape of the room we actually live in turns out to matter a great deal for how the rest of this story should be read, especially as we move from questions about measurement toward far more speculative questions about the deep architecture of reality itself, because it's here, at the edge of what experiment can currently test, that some physicists have proposed even more radical readings of why this wall exists at all. Readings that move from established physics into genuinely speculative territory. And it's important to be honest and clear about that shift as we make it. One of the more disciplined and mathematically serious ideas in this speculative territory is the holographic principle. First proposed in the early 1990s by Gerard T. Hooft and developed further by Leonard Susskind. The holographic principle grew out of studying black holes, and specifically out of a discovery made by Jacob Bekenstein and Stephen Hawking in the 1970s. Black holes have entropy, a measure of hidden information, and that entropy is proportional not to the volume of the black hole, as you might naively expect for any three-dimensional object, but to the surface area of its event horizon. This was a strange enough result on its own that physicists spent years trying to understand why nature would tie the information content of a three-dimensional object to a two-dimensional surface rather than to its full volume. T. Hooft and Susskind proposed a startling generalization. Perhaps this isn't a quirk unique to black holes, but a clue about the deep structure of reality itself. Perhaps all the information describing what happens inside any region of space can, in principle, be encoded on the boundaries surrounding that region, the way a hologram encodes a full three-dimensional image on a flat, two-dimensional piece of film. Jacob Bekenstein's original 1972 insight, which he arrived at partly by thinking carefully about the second law of thermodynamics, the principle that entropy, a measure of disorder, should never decrease in an isolated system, is worth pausing on, because it illustrates just how strange the connection between information and gravity turns out to be. Bekenstein noticed a troubling loophole. If you dropped a hot cup of coffee, full of disordered, entropy-carrying molecular motion, into a black hole, that entropy would seem to simply vanish from the observable universe, since nothing, according to general relativity, can ever escape from beyond a black hole's event horizon. If true, this would violate the second law of thermodynamics, one of the most sacred and thoroughly tested principles in all of physics. Bekenstein resolved the puzzle by proposing that black holes themselves must carry an entropy of their own, one that increases whenever anything falls in, exactly compensating for whatever entropy disappears from the outside universe. And remarkably, he showed that this black hole entropy had to be proportional to the surface area of the event horizon rather than to the black hole's volume, an idea Stephen Hawking initially resisted before eventually confirming and extending it himself, famously showing in 1974 that black holes must therefore slowly radiate energy, now called Hawking radiation, and eventually evaporate away entirely. Out of this exchange came a precise formula, sometimes called the Bekenstein bound, which places a firm, calculable upper limit on how much information can possibly be contained within any given region of space, a limit set entirely by the area of the boundary enclosing that region rather than by its volume. This is the direct ancestor of the holographic principle explored throughout this documentary, and it remains one of the very few places where quantum mechanics, gravity, and thermodynamics, three normally separate branches of physics, are forced to agree with one another with remarkable mathematical precision. This idea received a significant mathematical boost in 1997, when the physicist Juan Moldacena discovered a specific, precisely worked out example of exactly this kind of relationship, now called the ADS-CFT correspondence, showing a mathematical equivalence between a theory of gravity operating in a certain kind of curved, higher dimensional space and a completely different theory, without gravity, operating on the lower dimensional boundary of that space. This correspondence has become one of the most productive tools in modern theoretical physics, used to study everything from black hole information to the physics of exotic materials, precisely because it lets physicists translate difficult gravitational problems into more tractable problems in the boundary theory, and vice versa. It's important to be precise about what this does and doesn't establish. Maldaceno's discovery was proven within a specific, mathematically idealized model of spacetime, one with a particular geometry called anti-de Sitter space, which isn't actually the geometry of our own universe. Our universe appears to be closer to a different geometry called de Sitter space, associated with the accelerating expansion driven by dark energy, and no one has yet found an equally clean holographic correspondence for a universe like ours. So while the holographic principle is taken seriously as a deep hint about how quantum gravity might work, and has passed a number of non-trivial theoretical consistency checks, it remains, for our actual universe, a compelling hypothesis rather than a proven fact. If the holographic principle does turn out to describe our universe in some form, it would suggest something genuinely strange about the wall of unmeasurable information we've been exploring throughout this story. It would mean that the three-dimensional world of stars, planets, and people that we experience might be something like a projection, a kind of rendering, generated from information stored more fundamentally on a distant boundary. Perhaps something like the boundary of the observable universe itself. And if that's the architecture, then the finite amount of information that can be encoded on any boundary, calculated using the same entropy formula Bekenstein and Hawking developed for black holes, would put a hard, calculable limit on the total information content of any region of space, including the smallest, most local measurements we make in a laboratory. This has led some physicists, including Susskind himself and Jacob Bekenstein before his death in 2015, to speculate about something like a fundamental information density to the universe, sometimes described informally and somewhat loosely, using the metaphor of pixels, as if reality had a maximum resolution beyond which no additional detail could ever be encoded. No matter how you tried to measure it, this is exactly the point in the story where the metaphor of the simulation hypothesis tends to enter popular discussions. The idea, given a rigorous philosophical treatment by Nick Bostrom in a 2003 paper, that advanced civilizations might run enormous numbers of detailed simulations of conscious beings, making it statistically more likely that any given observer, including us, is living inside a simulation rather than in the one original base reality. It's worth being very clear and very careful here. There is no experimental evidence that we live in a simulation, and the fact that the universe has a finite information density, if the holographic principle turns out to be correct, does not, by itself, imply anything about computers, programmers, or artificial rendering. A finite information density is a statement about physics, about how much information a region of space can hold according to the mathematics of quantum gravity. It's an entirely separate question, a philosophical rather than a physical one. Whether that finite information density means anything is doing the computing. Some physicists have pointed out, only half-jokingly, that a universe with a finite information density and a universe that's actually a simulation would be observationally indistinguishable from each other in most conceivable tests, which is itself a philosophically interesting, if slightly uncomfortable, observation. But it isn't evidence for the simulation idea specifically. It's evidence, if the holographic principle holds up, for finiteness, which is a much narrower and more modest claim, a more grounded way to think about the relationship between the measurement wall and the holographic principle is to treat the finite information density as a kind of budget rather than a program. just as a photograph, no matter how detailed, is ultimately built from a finite number of pixels, and zooming in far enough eventually shows you the individual pixels themselves rather than more detail. A universe with finite information density might, at its smallest scales, simply run out of resolution to define additional facts, not because someone chose to render it cheaply, but because information itself, according to the deep laws of quantum gravity, cannot be packed more densely than a fixed amount per unit of boundary area. Under this reading, the wall isn't evidence of a program cutting corners. It's evidence, if this whole speculative framework is correct, that how much can be true about a given region of space has a hard upper bound built into the architecture of reality. The same way the speed of light puts a hard upper bound on how fast information can travel, not because nature is stingy, but because that's simply the shape of the laws we live inside. This raises one more question, more philosophical than experimental, but one that physicists occasionally do discuss seriously in conference talks and papers on the foundations of quantum theory. Is this information limit an accidental byproduct of deeper physics? The way a speed limit sign on a highway is a side effect of engineering constraints on the road? Or could it serve some kind of protective, structural role, preventing certain kinds of paradoxes or inconsistencies from ever arising within the theory? There's a genuinely interesting hint in this direction connected to the black hole information paradox, a puzzle that occupied Stephen Hawking and much of the theoretical physics community for decades. Hawking's own calculations in the 1970s suggested that black holes slowly evaporate by emitting radiation, now called Hawking radiation, and that this radiation appeared to carry no information about what fell into the black hole, seemingly destroying information in violation of a bedrock principle of quantum mechanics that information can never truly be lost, only scrambled. Decades of work, culminating in significant theoretical progress made between 2019 and 2022 by physicists, using techniques borrowed from the holographic correspondence, including work by Ahmed Al-Mehri, Netta Engel, and collaborators on what are called islands in the black hole interior, has provided strong evidence that information is, in fact, preserved, encoded in subtle correlations within the Hawking radiation in a way that earlier, simpler calculations had missed. This resolution, still being refined and debated today, suggests that nature does seem to have built-in mechanisms that prevent the kind of outright paradoxes that would arise if information could simply vanish. Whether the measurement wall discussed throughout this story serves a similarly protective role, quietly preventing some deeper inconsistency from ever occurring, or whether it's simply an incidental consequence of how quantum fields and space-time happen to be built, remains genuinely unresolved and reasonable. Expert physicists disagree about how to even frame the question. Before moving further into that shift in emphasis, it's worth lingering on just how strange the quantum computing story really is, because it puts the abstract wall we've been describing into a shape you can actually picture sitting on a laboratory bench. An ordinary computer stores information in bits, each one either a 0 or a 1, definite and stable. A quantum computer stores information in qubits, which can exist in a superposition of both states at once, and it's precisely this superposition, this refusal to settle into a single definite value until measured, that gives quantum computers their theoretical power for certain classes of problems, including the factoring of extremely large numbers, a task first shown to be dramatically speedable on a quantum computer by the mathematician Peter Shor in 1994. The trouble is that the very same fragility that makes superposition useful also makes it almost unbearably difficult to preserve. A qubit, sitting in superposition, is constantly being nudged by stray fluctuations in its environment, by tiny thermal vibrations in the material holding it, by stray photons, by cosmic rays passing through the surrounding building. And each of these nudges risks collapsing the delicate superposition into a definite, and usually wrong, classical value long before a calculation finishes. Companies and university laboratories working on this problem, including groups building superconducting qubits cooled to temperatures colder than the depths of interstellar space, and separate groups building qubits from individually trapped ions suspended in electromagnetic fields, have spent enormous effort on what's called quantum error correction, a set of techniques that spread a single piece of logical information across many physical qubits, so that errors in any individual qubit can be detected and corrected without ever directly measuring, and thereby destroying the fragile quantum information itself. This works, and it has improved dramatically over the past 2 decades. But it illustrates the wall in miniature. Engineers can build increasingly elaborate scaffolding to protect quantum information from noise, and they can push the achievable error rates down further and further. But nothing in that scaffolding removes the underlying uncertainty relation that makes qubits fragile in the first place. It only manages that fragility more and more cleverly, buying useful computation time out of a system that fundamental physics insists must remain delicate. This same fragility shows up in a different costume in the story of quantum sensing, a rapidly growing field that tries to turn the wall itself into a scientific tool rather than an obstacle, because a quantum system's uncertainty is so exquisitely sensitive to its surroundings. Researchers have learned to use carefully prepared quantum states as extraordinarily precise probes of gravity, magnetic fields, and even time itself. Atom interferometers, which use clouds of atoms cooled to temperatures just barely above absolute zero and then split into quantum superpositions along 2 different paths before being recombined, can now detect gravitational variations subtle enough to reveal hidden underground structures, shifts in groundwater, or even, in principle, the faint gravitational signature of a nearby mineral deposit. These devices work precisely because they operate right at the edge of the noise floor discussed earlier, meaning that any real signal has to be teased out from underneath the same zero-point fluctuations that limit LIGO's mirrors and that limit the coherence time of a quantum computer's qubits. Physicists building these instruments have effectively learned to read the static itself for information, treating the noise floor not as something to eliminate, which the underlying physics forbids anyway, but as a canvas whose subtle distortions can carry a signal if you know exactly how to look. It's a conceptual move worth sitting with, rather than fighting the wall head-on and losing. An entire branch of experimental physics has grown up learning to work with its exact contours instead. It helps too to notice how differently this shift plays out depending on which specific research community you're talking to. Because physics isn't really one monolithic enterprise chasing one shared question, but a sprawling collection of overlapping communities, each with its own relationship to the wall. Cosmologists mapping the large-scale structure of galaxies tend to encounter the wall as a distant boundary condition, something that shaped the earliest fractions of a second after the beginning of the universe and left faint statistical fingerprints in the cosmic microwave background, but something that mostly doesn't intrude on their day-to-day work, modeling how galaxies cluster and evolve over billions of years afterward. Condensed matter physicists studying exotic materials in a laboratory, by contrast, often encounter versions of the same underlying mathematics, borrowed through the holographic correspondence, as a genuinely useful calculational tool for describing real, measurable behavior in strange materials, with the deep philosophical questions about reality and simulation receding almost entirely into the background of a practical day's work. Quantum information theorists meanwhile, treat the wall almost as a design constraint, a set of hard limits that any future quantum computer or quantum communication network will always have to respect. The way an aerospace engineer treats the speed of sound as a design constraint rather than a philosophical puzzle. What almost everyone working in the foundations of physics does agree on, however, is that the last several years have marked a genuine and noticeable shift in emphasis away from asking what is really ultimately true down there and toward asking what can we rigorously calculate and verify about the statistical structure of what's knowable. This is a subtler shift than it might first sound. It doesn't mean physicists have given up on deep questions. It means the discipline has become more honest and more precise about which questions can be answered by current or foreseeable methods, and which questions, at least for now, can only be approached through mathematical consistency and indirect inference rather than direct measurement. Large research collaborations working on quantum gravity, from string theorists to loop quantum gravity researchers to a smaller but active community exploring alternative approaches like causal set theory and asymptotic safety, spend much of their time not trying to directly observe the Planck scale, which remains far beyond the reach of any conceivable near-term experiment, but trying to find indirect, testable consequences of their theories that show up at larger, accessible scales, small deviations in the cosmic microwave background, subtle effects in the propagation of high-energy cosmic rays over enormous distances, or tiny corrections to the behavior of black holes that future gravitational wave detectors, including planned upgrades to existing observatories and entirely new instruments like the space-based LISA mission, might eventually be sensitive enough to catch. There's a real and important humility in this shift, one that's worth sitting with rather than rushing past. For most of the history of science, progress has felt like steadily peeling back layers of a hidden picture, moving closer and closer to some final, complete truth waiting underneath everything. The measurement wall we've been tracing throughout this story suggests something different, that certain layers of reality may not be layers in the ordinary sense at all, waiting patiently to be peeled back by a sufficiently clever future experiment, but rather boundaries built into the very language physics uses to describe existence. Boundaries where the usual meanings of words like position, time, and fact may simply stop applying in the way our intuition, built entirely from experience with the ordinary, everyday-sized world, expects them to. None of this should be read as an argument for giving up on understanding the universe, and it's worth being direct about that, because it would be easy to walk away from a story like this feeling that physics has hit some kind of dead end. It hasn't. If anything, the past few decades have produced one breakthrough after another precisely by taking these limits seriously rather than ignoring them. The detection of gravitational waves by and later by its European counterpart, Virgo, opened an entirely new observational channel for studying the universe, one that had been theoretically anticipated for a century but only became technologically achievable once engineers found ways to work skillfully with, rather than against, the quantum noise floor. The Event Horizon Telescope's 2019 image of the black hole at the center of the galaxy Messier 87 and its 2022 image of Sagittarius A star at the center of our own Milky Way required physicists to carefully account for exactly the kind of information, limits, and quantum considerations discussed throughout this story when interpreting what the telescope array could and couldn't resolve. Even the ongoing search for a theory of quantum gravity, still incomplete after nearly a century of effort by some of the most capable minds in the history of science, has produced enormously valuable byproducts along the way, including the holographic correspondence itself, which has found surprising applications in condensed matter physics, describing the behavior of exotic materials that have nothing directly to do with black holes or cosmology. The right way to think about the wall, then, isn't as a locked door that ends the story of discovery, but as a genuinely new kind of landscape that changes what discovery even means once you get close enough to it. In the classical picture of science, discovery meant finding out a fact that was always there, waiting. In this new landscape, at least at the deepest scales, physics has probed. Discovery increasingly means characterizing precisely what kinds of facts can exist at all, what the statistical structure of possibility looks like, and what mathematical consistency requires, even in places where no direct experiment may ever be able to reach. That's a different kind of knowledge than a photograph of Jupiter's moons or a decoded genome. But it's knowledge nonetheless, hard-won, rigorously tested wherever testing is possible, and genuinely illuminating about the shape of the universe we live inside. There's also something worth noticing about how this story connects back to something far more human than equations and detectors. Every civilization that has looked up at the night sky has eventually asked some version of the same question. Is there a bottom to this? Some final layer where everything finally makes complete, transparent sense. Ancient philosophers debated whether matter was infinitely divisible or built from indivisible atoms, a word that comes directly from the Greek for uncuttable. It took over 2,000 years, and the tools of 20th century physics, to discover that atoms themselves are built from smaller pieces after all, and those pieces from smaller pieces still. Quarks and electrons that, as far as current experiments can tell, show no internal structure at all, at least not at the energies humanity has been able to probe so far, up to the roughly 13 trillion electron volts, reached by the Large Hadron Collider at CERN. Each time humanity has assumed it found the final, uncuttable layer, nature has occasionally revealed one more layer underneath. The measurement wall discussed throughout this story might be different from those earlier surprises. Not simply one more layer waiting to be found, but potentially the edge of the entire concept of layers as applied to reality. Or it might not be. It remains entirely possible that some future theory will find a way past it that no one today has imagined. The way relativity and quantum mechanics themselves would have seemed like impossible fantasies to a physicist working in 1850. Genuine intellectual honesty requires holding both possibilities at once. The wall might be permanent, or it might simply be the current edge of what 19th and 20th century mathematics happened to be equipped to describe, waiting for a conceptual revolution no one has had yet. What does seem clear, and what most physicists working seriously in these fields would agree with, even amid all their other disagreements, is that living with this uncertainty gracefully, rather than either denying it or being paralyzed by it, has become an important part of what it means to do fundamental physics in the 21st century. Earlier generations of physicists sometimes spoke as though the ultimate goal was a final theory of everything that would answer every question about reality in one elegant equation. That language still appears occasionally, but it's used more cautiously now, more provisionally, by physicists who have spent their careers watching one supposedly final boundary after another turn out to have its own subtleties, its own genuine limits, its own honest uncertainties that no amount of additional cleverness has been able to remove. The goal has shifted, gradually and without much fanfare, from finding the final answer to mapping, with as much precision and honesty as possible, exactly where the questions themselves stop making sense, and why it's worth remembering that this isn't the first time physics has been forced through a humbling adjustment of this kind, and looking at the earlier ones can help put the current moment into perspective. In the 1800s, following the enormous success of Newtonian mechanics in predicting the motions of planets, comets, and even the existence of Neptune before it was ever directly observed. Many physicists genuinely believed the discipline was nearing completion, that only a few loose ends, decimal points to be refined, remained before physics would be essentially finished. Some of those loose ends, including a small, nagging discrepancy in the orbit of Mercury that Newtonian gravity couldn't quite explain, and the strange results of the Michelson-Morley experiment in 1887, which failed to detect the motion of the Earth through a hypothesized medium called the luminiferous ether that light was assumed to travel through, turned out not to be minor details at all. They were the first cracks revealing that Newtonian mechanics, spectacularly successful as it was not the final word, and resolving them required Einstein's special and general theories of relativity, ideas so different from everyday intuition that they required physicists to abandon comfortable assumptions about absolute space, absolute time, and even the straightforward addition of velocities that had seemed self-evidently true for over 2 centuries. Quantum mechanics arrived barely 2 decades later and demanded an even larger sacrifice of intuition, asking physicists to give up not just absolute space and time, but the very idea that particles have definite properties independent of measurement at all. Each of these historical humblings felt, to the physicists living through it, like an ending, a wall, a point beyond which the discipline simply could not proceed without abandoning what had seemed like bedrock common sense. Each time, physics didn't end. It reorganized itself around a deeper, stranger, but ultimately more accurate picture of reality, and went on to make discoveries the previous generation couldn't have imagined. There's no guarantee that the measurement wall described throughout this documentary will follow the same pattern, resolving itself eventually into some deeper theory that current physicists simply haven't found yet. It's entirely possible, and taken seriously by a meaningful fraction of the physics community, that this particular wall really is different in kind from earlier ones, a genuine, permanent boundary on what can ever be known, rather than merely the current edge of an incomplete theory waiting for its own Einstein or Planck to come along and dissolve it into something clearer. But the history of the discipline at least counsels against excessive certainty in either direction. The physicists who assumed, in the 1890s, that only minor details remained to be worked out were embarrassingly wrong. And it's worth remembering that humility when tempted to declare, with full confidence, that today's wall is the final one. At the same time, it would be equally dishonest to pretend that the deep mathematical and experimental reasons behind today's wall are flimsy or temporary, when in fact they rest on some of the most thoroughly tested, most independently confirmed physics ever produced. From Bell's inequality violations, replicated in dozens of laboratories, to the direct detection of gravitational waves predicted a century in advance, the honest position, the one most careful physicists actually hold, sits somewhere between false certainty and false humility. Today's wall is real, well supported by evidence, and worth taking seriously as possibly permanent, while remaining, like every wall in the history of this remarkably persistent discipline, provisionally open to being redrawn by whatever comes next. There's a strange kind of beauty in that shift, one that's easy to miss if you only think about physics as a race toward a finish line, a universe where everything could eventually be known, given enough patience and enough clever instruments, would in some sense be a smaller, more mechanical place than the universe we actually seem to inhabit. The universe suggested by nearly a century of quantum experiments, from the double-slit pattern that first surprised physicists in the early 20th century to the delayed choice, quantum erasers, and Wigner's friend experiments of the 21st, is one where reality itself resists being fully pinned down by any single, external observer, where facts come into being through relationship and context, rather than existing as a passive backdrop waiting to be photographed. That's a genuinely different picture of existence than the one most of us grow up assuming, closer, in some ways, to the deep interconnectedness poets and philosophers have gestured toward for millennia than to the cold, clockwork universe that early modern science sometimes seemed to promise. It's worth taking a moment to look specifically at where the next real tests of all this are actually likely to come from. Because this isn't a story that ends in pure philosophical speculation with no experimental path forward. Several major instruments, either recently operating or currently under serious development, are aimed, at least in part, at probing the edges of exactly the questions this documentary has been exploring. The space-based laser interferometer, space antenna, generally known by its acronym, is a mission under development by the European Space Agency in partnership with contributions from other agencies. Designed to place 3 spacecraft in a triangular formation separated by millions of kilometers, using laser beams to detect gravitational waves at frequencies far lower than ground-based detectors like LIGO can reach, because its arms are so much longer, and because it operates far from the seismic noise that limits ground-based detectors. This mission is expected to be sensitive to gravitational waves from sources, including the mergers of enormous black holes at the centers of colliding galaxies, and possibly even to subtle signals from the earliest, most extreme moments after the beginning of the universe, moments when quantum gravitational effects, of exactly the kind discussed throughout this documentary, would have been most pronounced. On the ground, meanwhile, physicists in Europe are developing a next-generation gravitational wave observatory known as the Einstein Telescope, planned as an underground facility specifically designed to minimize the environmental vibrations that limit current detectors. While researchers in the United States are pursuing a parallel next-generation design called Cosmic Explorer, both instruments are intended to push gravitational wave astronomy an entire order of magnitude or more, beyond the sensitivity of today's LIGO and Virgo detectors, which would allow physicists to observe black hole mergers occurring much further back in cosmic history, closer to the very early universe, and to test general relativity itself in the extreme, strongly curved spacetime near a black hole's event horizon with far greater precision than is currently possible. Any subtle deviation from Einstein's predictions in that regime, a slightly different ringing pattern as a newly merged black hole settles down, for instance, could provide the first genuine experimental foothold on quantum gravity, the very framework that would ultimately explain or dissolve the measurement wall this documentary has been describing. Cosmology offers another promising avenue, somewhat indirect but potentially powerful. The James Webb Space Telescope, which began science operations in 2022, was designed primarily to observe the earliest galaxies and the atmospheres of distant exoplanets. But the exquisite precision of its instruments has also made it useful for constraining certain models of quantum gravity that predict specific tiny distortions in the light arriving from extremely distant, extremely early sources. Distortions that would accumulate detectably only after light has traveled across nearly the entire observable universe. Separately, physicists analyzing the cosmic microwave background, the faint afterglow of the early universe, first discovered accidentally in 1965 by Arno Penzias and Robert Wilson, and mapped with ever-increasing precision by later missions, including the Wilkinson Microwave Anisotropy Probe and the European Space Agency's Planck satellite, have searched carefully for subtle statistical imprints that some quantum gravity models predict should have been left behind by Planck-scale physics operating during the universe's first fraction of a second. So far, no such signature has been conclusively detected, and the cosmic microwave background data remains consistent with simpler, standard cosmological models. But each new generation of more sensitive measurement tightens the constraints on what any successful theory of quantum gravity is allowed to predict, gradually narrowing the space of viable ideas, even without a direct detection. There's also a quieter, tabletop side to this search, running in parallel with these enormous space missions and international collaborations. Small teams of experimentalists around the world are building increasingly delicate tests, using massive quantum superpositions of exactly the kind discussed earlier in connection with Roger Penrose's proposed gravitationally induced collapse, using techniques like optically levitated nanoparticles held in place by focused laser light in a near-perfect vacuum, isolated as thoroughly as current technology allows from the decohering influence of their surroundings. These experiments operate on a minuscule budget compared to a space mission or an underground gravitational wave observatory, often run by small university groups rather than vast international collaborations. But they're aimed at exactly the same fundamental question: does quantum superposition genuinely persist all the way up to increasingly macroscopic scales, exactly as standard quantum mechanics predicts? Or does something new happen, some genuine physical collapse mechanism, once a system crosses a certain threshold of mass? It's a rare and appealing feature of this particular frontier of physics that some of its most important open questions can be probed both by multi-billion-dollar international space missions and by a small, resourceful laboratory group with a good vacuum chamber and a clever idea. And both approaches are, right now, actively narrowing down which of several serious theoretical possibilities might turn out to be correct. None of the open questions this story has touched on are close to fully resolved. And that's exactly what makes this such an active and exciting area of research, rather than a settled chapter of physics history. Physicists still don't know how to unify quantum mechanics and general relativity into a single, complete, experimentally confirmed theory, despite decades of extraordinarily sophisticated work from string theorists, loop, quantum gravity researchers, and others. They don't know for certain whether the holographic principle applies to our specific universe, with its accelerating, dark energy-driven expansion, the way it demonstrably applies to the idealized mathematical spacetimes where it was first proven. They don't know whether the measurement wall reflects some deep, protective logic built into the structure of reality, or whether it's simply an incidental consequence of how quantum fields happen to interact with curved spacetime, with no deeper purpose behind it at all. And they don't know, perhaps most importantly, whether some future conceptual breakthrough, the kind that arrives only once or twice a century and reshapes everything downstream of it, will eventually show that today's wall was simply the edge of 20th and 21st century mathematics, rather than the true edge of nature itself. What they do know, with a level of confidence built on nearly a century of relentless experimental testing, is that this uncertainty is not a failure of effort, not a gap that better funding or smarter graduate students will simply close through incremental progress, the way earlier generations closed the gap on the structure of the atom or the sequence of the human genome. It appears to be, as best as the most careful, most rigorously tested physics available today can tell, a genuine and fundamental feature of the universe we happen to live inside, one written into the relationship between energy and distance, between measurement and disturbance, between an observer and the observed. And there's something quietly remarkable, rather than defeating, about a species that evolved on a single small planet, orbiting an unremarkable star, in an ordinary galaxy among hundreds of billions of others, managing to reach far enough with mathematics and instrumentation to map the precise shape and location of the edge of its own knowledge, even if it can never step across that edge to see what, if anything, lies on the other side. That mapping, careful, honest, endlessly revised in light of new evidence, is itself one of the most impressive things our species has ever done. And the story of where it leads next is still very much being written. One experiment, one calculation, and one carefully reasoned argument at a time.